Right, so this is lecture 10. We're going to have a look at unions and partitions. There's quite a lot of abstract stuff in here, along with some specific examples that we can look at to try and make sure we understand. So here's a first question to get you started. How many different subsets does this set have? So let's let you think about that one. And I'll get you to vote in a bit. So feel free to talk amongst yourselves if you like. And I'll just give you a minute to work out how many different subsets it's got. Okay, if you haven't voted yet, please vote now. Let's reload that one. Okay, so we've got quite a majority in favour of C, but we've got a few other answers as well. Now, there are various reasons why one might miscount this. C is correct. There are indeed 8 subsets. Now, what might make you miscount by 1 is forgetting about the empty set, which counts. So don't forget that the empty set is a subset of A, and A is a subset of A as well. Those are the two extreme subsets, and the other ones are in between. Now, you can list them all, and you might miss one if you forget that the empty set and A count as subsets of A. But there's a more general reason, which I'm about to tell you, why you know it's going to be 8. It's because 8 is equal to 2 cubed. A's got 3 elements. And 2 cubed equals 8. So why is it 2 to the number of elements? I'm going to tell you. Don't do that. So if you take a general set, if we take a more general set, and X might be a big set now, though for the moment we'll look at ones with only finitely many elements. But X could be the real numbers, in which case the real numbers have got an awful lot of subsets, a huge number. The natural numbers have slightly fewer subsets, but it's still an infinite number. And finite sets don't have that many subsets, okay? But here's our different notations for it. This P of X, sometimes I'll write that, when I write that, I end up with a curly P of X like this. So some sort of script P of X, calligraphic P, or a curly P, anything like that will do. That's a set of all subsets of X, or the collection of all subsets of X, of which there'll be lots. Also written 2 to the X, which is very suggestive. Now, a finite set is a set which has only got finitely many elements in. The empty set counts. The empty set has got no elements. The empty set has no elements, so it's got one subset. I'll just note that the power set of the empty set is the set of all subsets of the empty set. So it's this. The empty set has got one subset. I'll note that the empty set has number of elements is 0. And the power set of the empty set has 1 element. Because the empty set is an object. So this thing here has got one object in it. The object that's in it happens to be the empty set, but that's okay. It's a mathematical object. So there's one element in this set. Often causes confusion. Now, so the empty set is special, but I note that even so, 2 to the 0 is equal to 1, which is a good start. However, we're normally interested in finite sets which have got some elements in. So say you've got n elements in, non-empty, so n is a natural number. And then you could list them. If you're going to list x like this, then there better not be any repeats, because otherwise, since we said that x has got n different elements in it, if you write x equals x1, x2, xn, you'd normally be allowed repeats. But since I'm saying it's got exactly n elements in, these must all be different. Okay, so I've written it now so they're all different. They didn't have to be numbers, so I'm not claiming that x1's less than x2 or anything like that. They could be anything. These elements could be sets. One of these elements might be the empty set, and another element might be a completely different set. Could be anything. Doesn't matter. It's x has got n things in it. And now, how many different subsets does x have? Well, the answer is 2 to the n. Why is that? Well, you have to make a decision for each element, whether it's in the set or not in the set, and that's decisive. So for every element of x, you've got two choices. Are you going to put it in the subset or leave it out of the subset? If you change any of your choices, it changes which subset you get. So you get two choices for each element, in or out, and so on, in or out, n choices, so you get two choices for each element of x. Well, there's one choice with two possible options. In the subset or out. In the subset or not. Now, if you decide for all of the elements to have it not in the subset, then you're going to get the empty set, which is the smallest possible subset of x. If for every element of x you decide that it is going to be in the subset, then you're going to end up with the whole of x, which is the biggest possible subset of x. Otherwise, you'll get something in between where you chose to put some of the elements in the subset and keep some of the elements out of it. But you get, let's just have another page. So the number of possible subsets that's 2 times 2 times, you're making n choices. So you get 2 multiplied by itself n times, which is equal to 2 to the n. Alternatively, you can prove it by induction. So I quite like this way of just saying it. You've got two choices for each element, so there's 2 to the n overall. But you can prove it by induction if you like. Let's make that as an exercise. So it's alternative proof. Prove this formula by induction on n. The way it works is, okay, we already did it for no elements, but maybe that's a special case. If you've got one element, there's two possible subsets. Either you have the element in which case it's the whole thing, or you don't have the element in, and then it's empty. So if you've got one element, there's only two possible subsets. If you know what's going on with n minus 1 elements, then if you want to see how many subsets the n element set's got, well, you can say, we'll have those subsets which have got the last element in, and those which don't have the last element in. And there's 2 to the n minus 1 of each by induction. But I'll leave that for you to think about and decide which your favourite is. Anyway, so now we know how many subsets a given set has. It's just 2 to the number of elements. Unfortunately, if the set's got infinitely many elements, then you're talking 2 to the infinity, which doesn't make a lot of sense, but which turns out to be a bigger infinity. And we'll see something about that at the end of the module. So if you've got infinitely many elements in your set, and you take the set of all subsets of it, it turns out that that's always a bigger infinity than the infinity you started with, which is quite interesting. And we'll say more about that at the end of the module. Okay, unions of collections of sets. We've looked at a union of 2 sets, and we looked at unions of a few sets, and I said earlier, and we're going to look at infinite unions later. So here we are, we're going to do it. Suppose you've got lots of sets, a whole sequence of sets. So here we are. I'm going to give you one example. For every natural number, so there's infinitely many of these, so for n equals 1, 2, 3, 4, my set AN will have just 2 elements. It's going to have in it minus n and plus n. Okay? Now, I'm going to take the union of all of them, which has got various notations. Here are 3 ways of doing it. The union of all of these sets. The union from n equals 1 up to infinity, this is like series notation. It doesn't mean there's a set A infinity. It means that I'm taking the union over all natural numbers of AN. So I'm taking the union of A1, A2, A3, A4, all of them. You're also allowed to write it like this. The union of all of the AN where n runs through natural numbers. These 3 all mean the same thing, and they also mean it's equal to those x such that there exists a natural number n such that x is in AN, using our exist notation. But it just means that we're looking for x, those x which are in at least one of the sets. The sets are all subsets of the integers, so we can't get anything in here that isn't an integer. So if you wanted to, you could say it's those integers x which are in at least one of the sets, and it wouldn't change anything. But if you weren't sure in advance, you'd just say it's those x which are in at least one of the sets. So I wonder if anybody can just see off the top of their head what this set is. Yeah? The non-zero integers, exactly. You get the non-zero integers here. So the answer is z take away 0, right? The non-zero integers. Why is that? Well, first of all, you might want to check that 0 isn't in any of these sets, but you look at it. n was going for the natural numbers. Remember, naught's not a natural number, so naught is not in any of these sets. So it's not true that there exists a natural number with naught in AN. So naught is not in this union. But every other integer is, because whether the integer is positive or negative, it's going to turn up in one of these sets. In fact, it's going to turn up in exactly one of these sets. No, exactly 2 of these sets, if it's a non-zero integer. Exactly one of these sets? Exactly one of these sets. Each integer is going to be in exactly one of these sets, that's right. If it's negative, it'll turn up in the positive one, yes. It doesn't matter. Anyway, now I think I finally got it right. Anyway, thanks for that. Yes, it's a set of non-zero integers. I'll leave that as an exercise for you to fill in the details. I've just described it in words. We'll do another one properly. We're going to do a slightly harder one properly below. So I can leave this one that's relatively easy for you to do, and you'll probably get it right. Now, even though there's infinitely many sets here, it's a relatively small infinite number. It's only 1 for every natural number. And we can do better than that. We can go to very big collections of sets if we want. So it's a special case of what we call an index collection. And we can index collections by bigger sets, like the open interval 0 to infinity, the positive real numbers here. There's a lot of positive real numbers. There's uncountably many, as we'll see at the end of the module. So it's a lot more than the natural numbers. But it's still very easy to to assign a set for each of these. Like if I say for each positive real number r, I'm going to have a set called a sub r, which will be those real numbers x, so that modulus of x is less than r, and I will observe that this is just equal to the open interval minus r up to r. Okay, that's the same thing. Now you can see that if you vary r through the positive real numbers, you get different sets. So that's a lot of different sets, and it's an indexed collection of sets. And now you can take the union of them all, the union over r in naught infinity, over all positive real numbers of these sets AR. You know, we're going to keep changing which sets we're looking at. At the moment, this is what AR is. The union of all these, I claim it's a whole real number, all real numbers. Remember, it's also the same as, come back. It's those x such that there exists an r in the positive reals with x in minus r. Now, r is allowed to depend on x, okay? So, to figure out whether x is in here, we're supposed to decide if there's any r that works. Now, if you want to see what you get, you notice that, for example, note that x is in minus r if r is equal to, say, mod x plus 1. I've given you a formula for r in terms of x. What I'm proving is that for all real numbers x, there exists an r so that x is in that interval. For all x in R, there exists an R greater than naught such that x is in minus RR. This exists R greater than naught. There's a convention if you say exists R greater than naught, you mean a positive real number. I'm not allowing infinity or anything like that. Okay? And to prove this, I want to show that that for all R, this exists thing is true. Now, to prove an exists thing is true, you only have to find one example, but it's allowed to depend on any variables mentioned earlier. So this specific example, r equals mod x plus 1, doesn't look specific because it's got an x in it. But x was already mentioned earlier. So r is allowed to depend on x. And now you can check that, that as long as you make r, any r strictly bigger than mod x will do, and x will then be between minus r and r. Okay. And then, more abstractly, you just take any old collection of sets, and you can take the union of a collection of sets and get another set. And we'll do that sometimes. Okay? So sometimes we'll be a bit abstract, but the union of your collection is those x which are in at least one of the things in the collection. And you could also, you could write it like union of the collection, or you can write it the union over all A in the collection of A. It's the same thing. Okay. Pretty abstract, but let's have a question for you to think about. Your task, based on the sort of thing we've been looking at before, is to try and figure out what this set is. And I'll give you that it's guaranteed to be a subset of R. All right? So we're using closed interval notation, so I'll remind you that AB is equal to x in R for which A less than equal to X less than equal to B. We'll allow A equal B, by the way, because the first n here, A is actually equal to B, where you just get 1 point. But the later ones are slightly bigger intervals. A is definitely a subset of R. I'll give you that for free. If you take a union of subsets of R, you can't get something that isn't a subset of R. You can't escape from a set by taking unions of subsets of it. So that bit comes for free. So you're trying to figure out which real numbers are in this, and now I'm going to let you discuss that. You have to try and figure out for which real numbers is it true that you're in at least one of these sets. Okay, so you discuss that for a couple of minutes. I'm going to come round and see how you're getting on. Don't vote yet, I've got to zero the votes. Okay, let's see what people have gone for. I'll have to refresh that. Okay, so we've got a big majority in favour of D. I've got some requests to explain the question again. Hopefully, in explaining the answer, I will explain the question. So D is correct. So congratulations. You've worked out what this set is. So we know it's a subset of R. We just have to decide which real numbers are in there. Now notice, for all natural numbers n, we have 1 over n is greater than 0. So, in particular, 0 is not in 1 over n, and nor are any negative numbers. So the first thing is you've eliminated straight away any non-positive real numbers. So 0 and negative numbers are not in any of these sets. You get that for free straight away. So all you have to do, given that we know that only real numbers can be in there, all you have to do is show that the rest of the real numbers, the positive real numbers, are there. So what we're going to do is we're going to focus. This is enough to prove, because we know it's a subset of R that's got no non-positive real numbers in, we now know it's a subset of the open interval 0 to infinity. So what we get immediately is that A is a subset of the positive real numbers. So the question is, why do you get all of them? So to finish, we're going to show that 0 to infinity is a subset of A. And I'll do this by a more standard approach, which is to say let x be in 0 to infinity. Okay? So x is a positive real number. Since x is greater than 0, we can find an n1 in the natural numbers with 1 over n1 smaller than x. Smaller or equal will do, actually. Now, various approaches to that. One is, you probably know by now that the sequence 1 over n tends to 0. So eventually you'll get one that's less than x. If you don't know that, then I can tell you how far you've got to go. Any integer that's greater than 1 over x will do. Okay, 1 over x is also a positive real number, but you can beat that by some big integer. So that's what you do to get n1. That's to make sure that x is not outside the interval by being too far to the left. I also want to make sure that it's not too far to the right. We can also choose, again, x is a positive real number. It might be a big positive real number, but we can still beat it by an integer. So we can choose an n2 in the natural numbers with n2 greater than x. Greater or equal would do. Okay. But I just want to point out you can always beat you can beat a real number using a suitably large integer. Hopefully you'll know enough from ACF, if not now then later, to be convinced that this is true. Okay, then set n equal the max of n1 and n2. And then we win with both. One over n is actually less than x is less than n. So certainly x is in the closed interval 1 over n. It's actually in the open interval, but I decided to go for overkill. Okay? If you want to go back and use less than or equal here, that's fine. If you want to use greater or equal here, that's fine. But I've more than proved that x is in the closed interval. And so it's in at least one of them, and so it's in A. Come on. It's refusing to listen to me. There we go. So x is in A because to be in A means you have to be in at least one of the sets. This shows you in at least one of the sets properly. So what did we do? We said let x be in this set, then it's in A. That's the standard proof structure for proving that something's a subset of A. If you start with let x in here, your only assumption is that x is in that set. Your conclusion is that it's in this set. That's the correct proof structure for showing that everything in here is in here. So that tells you that the positive real numbers is a subset of A. And the rest follows from that. We've got both inclusions. If you've got set inclusions both ways round, then they have to be equal. So equality follows. In case you've forgotten, we'd shown that A was a subset of 0 to infinity, though we did it in a rather brief way. We said that at the very beginning. We saw immediately that A couldn't have anything that wasn't a positive real number in it. And at the end, we've shown that all the positive real numbers are in A. So we finished. Any questions about that union proof? Well, do let me know if you've got any. But for the moment, we'll move on to talk about partitions. Now, this is a bit like the stuff that we were talking about at the end last time, where didn't have much time as I wanted. So this will start to fill in some of the stuff, and again in lecture 11 we'll do more on this again. So hopefully by the time we've done all that, we'll be happy with it. Right, so one of the things I said we could do was to split the integers up into the odd integers and the even integers, using our definition. The even integers were those which were divisible by 2. Divisible by 2 was also what we called congruent to 0 modulo 2. Congruent to 0 modulo 2 means the remainder is 0 when you divide by 2. Congruent to 1 modulo 2 means the remainder is 1 when you divide by 2. That's the same as being odd. Okay? So here we have the odd integers and the even integers. And every integer is either even or odd. And it can't be both either. Okay? And also, there are plenty of even integers and there are plenty of odd integers. So this gives an example of what's called a partition of the integers. A partition of Z into 2 pieces this time. So the partition is a collection of sets. In this case, there's 2. One is a set of odd integers and the other is a set of even integers. And between them, these are 2 sets that don't overlap. Neither are empty, but between them, they give you all of the integers. So in the abstract, here's what a partition is. A partition of a set S, and I don't want to bring in the empty set this time because it's just going to bring confusion. I don't want to talk about partitions of the empty set. So we'll have S to be a non-empty set, and I want to say what is a partition of it. In the abstract, is a collection, that's just a set, of non-empty subsets of S, such that every X in the set is in exactly one of them. So we're going to be chopping up the set into pieces. There could be finitely many pieces, there could be infinitely many pieces, there can even be just one piece. The pieces could be of varying different sizes. Each of the pieces we chop it into should be non-empty. None of the pieces must overlap, and you must get the whole set from this. Now, before I go through these 3 comments, let me just draw you a picture, because some people like pictures. I'm going to consider S to be the set with 1, 3, 7, and 13 in it, just for example. But I'll draw it like this, okay? Here's S. S is your set, and it's got in it 1, 3, 7, and 13. And now I'm asked to partition the set S up into pieces. Well, this is like saying, choose some of them to throw into one piece. Maybe I'll put 1 and 3 in the same thing. And then, to avoid it being too boring, I'll use another couple of pieces, each of which has only got 1 in. And this gives you C equal to, I've chopped up into 3 pieces. Each of the pieces is a subset of S. One of the pieces has got 1 and 3 in it. Another piece has just got 7 in it. And another piece has just got 13 in it. I've chopped them into 3 pieces. Each of the sets is non-empty. Is that right? Yes. There's 2 in this one, 1 in this one, 1 in this. 13 has got 1 element. Yes, 1 element in there. I just confused myself. Yeah. So I've got 3 different pieces of varying sizes. Together, everything in S is there. S is the union of C. That's the bit that says that everything in the set is in at least one of them. But because they don't overlap, this pairwise disjoint means non-overlapping pieces, means that there's nothing that any of the relevant sets share. Because of that non-overlapping bit, not only is everything in S in at least one of these sets, everything in S is also in at most one of the sets. Otherwise, they wouldn't be non-overlapping. So a partition is quite a strict thing. I'm not allowed to use the empty set. I have to throw everything into exactly one of these pieces, and that's how I form a partition. Now, there's quite a few other partitions of S. and that will be on the second practice coursework to figure out how many different partitions there are. I think it's for a 4-element set. You could have fun thinking about that. In a moment, I'm going to let you think about it for 3 points. So here we are. You've got a set this time with just 3 elements, and your task is to figure out how many different partitions there are. You can list them all. There really aren't very many. So without trying to find a clever formula, see if you can list them all. And talk amongst yourselves, and we'll see what you come up with. And I'll just zero the votes while I'm at it. Okay, I've deleted all the votes, so you can vote whenever you like. And I'll pause the vote. Just in case it's of any help, you'll note that you have to chop this set up into pieces, and you might ask how many pieces can you chop it up into. You're allowed to chop it up into 1 piece. You could chop it up into 3 pieces, or you could chop it up into 2 pieces. There won't be any other number of pieces you could chop it up into. Let's refresh this, see what people have gone for. Okay, we've got a big majority in favour of B, with some other answers. And B is correct. Okay, here's your set S. You've got to chop S up into pieces. The pieces aren't allowed to overlap. They aren't allowed to be empty. Now, one thing you could do is use 1 piece. So if you decide to put them all in the same piece, we get C1 is just S, okay, which is this one. Remember, it's got to be a set of sets. So this set has got 1 set in it. This set has got 1 element, and that element is the set S. That's the one where you chop it up into 1 piece. You can also chop it up into 3 pieces. This looks also a bit like S. So notice, S has got 3 elements, C1 has got 1 element. C2 has got 3 elements, 1 for every element of S. So what picture is that? That's the one where I put each element in its own piece, okay? But this is not equal to S, even though it's got 1 element for every element of S, because S, the elements of S are numbers, the elements of C2 are sets. And there is a difference between a set and a number, generally, depending on your definition of number. So this is subtly different from S itself. And then there's 3 more. The other 3 are the ones where you put 2 in one set and 1 in the other. And the 3 of these, basically you have to decide which one's going to be on its own. So we can have C3 equal, put 1 and 3 together and leave 6 on its own. That's a partition into two pieces of varying sizes. C4, I'll put 1 on its own and put 3 and 6 together. And C5, I'll put 3 on its own and 1 and 6 together. And it's not hard to prove that there aren't any others at all. Okay, so that's it. There's only 5 different ways to partition a 3-element set. By the time you get to 4 elements, there's a few more. Trying to figure out a formula for how many you get is a bit tricky. But there are various inductive formulae for it so that you can build up from earlier versions. But I'll leave you to think about that. And you can think about the 4-element one in advance, but you'll get to see it on the question sheet. I'll put solutions to the first practice coursework on the web. I'll put those solutions on this afternoon. The marked work, unfortunately, the markers haven't quite finished, so that should be available on Monday. It may, whether it'll be available, I think I'll probably just put it in my pigeonhole on Monday, the marked work, and I'll send an email around. I'll also make solutions available to some of the Dr. Zacharias question sheets, because that's a lot of extra practice you might want to do. I'm sure you're all practicing really heavily on lots of questions by now in preparation for the class test. Okay, so we'll stop there for now, and we'll start the workshop at 4 o'clock.